Welcome to the Here's a Summer of Programming Languages. Have you ever asked yourself, am I using a suitable programming language for this task? Then this collection of introductions to programming languages used in research software engineering has something for you.
Hi there, my name is Brad Chamberlain. I'm a distinguished technologist at Hewlett Packard Enterprise, and I'm the technical lead of the Chapel Programming Language project, which I'll be telling you about today, and one of the founding members of the project. This talk is part of the HiRSE Summer of Programming Languages seminar series, and we greatly appreciate the organizers of this series for inviting us to be a part of it. The title of my talk is Writing Parallel Research Software in Chapel. I think of the main point of this series as being to answer the question, why would someone consider using this language rather than all the other languages in the world? So starting with that, why would one consider programming in Chapel? The very short answer is that it's one of the few programming languages that was designed for scalable parallel computing from the start. The rest of this talk will give an answer in more detail and tell you more about what Chapel is. Before I get too far, though, I want to define my terms. Not everyone watching this may know what scalable parallel computing is, so let's just talk about that real quick. And if you already know, bear with me or skip ahead a few minutes. So what is scalable parallel computing? First of all, let's define parallel computing. My definition of that is when you use the processors and memories of multiple compute resources, multiple computers, and you use those together to solve a problem cooperatively. Now, why might you do this? The main reason that I think people start doing it is that it allows you to run a program faster than you might be able to otherwise. So for example, this little cartoon is a very simple picture of a computer. It has processor cores, 4 in this case. Maybe this is like a 4-core laptop. And it's got some memory in orange. You can see some data allocated there. Typically, when we write programs, we write serial or sequential programs, and those only run on a single processor core at a time. But most processors today have multiple cores, and so there's the opportunity to actually run multiple tasks on them simultaneously. And so if I could write my program in such a way that it made use of all 4 processor cores, then there's the potential I could run it 4 times faster, and that might be nice. Similarly, if I run using not just a single computer, but multiple computers or compute nodes connected by some sort of network, then I can take advantage of the processor cores across many computers and perhaps go even faster. So in this picture, for example, I've got 16 cores. Maybe if I can use all of them, I can go 16 times faster. Later on in this talk, we'll see some performance results that go thousands and hundreds of thousands times faster. The other reason one might do parallel computing is that you can harness the memories of multiple compute nodes as well. So maybe I was constrained to a certain problem size if I was only using my laptop, but once I string these 4 compute nodes together, I can use all of their memories together and run a problem size that's potentially 4 times larger. So that's parallel computing and why we might do it. Now, I've been using the term scalable parallel computing. What that means to me is that as more processors and memory are added to the program, the benefits will continue to increase. This isn't always the case. Some programs by nature at some point might not be able to scale any further as you add more processors and memory, but this is a good property to shoot for. It's certainly one that we strive for. And this notion is very important for a lot of research software where you're perhaps simulating a large system, some aspect of the physical world or the universe, and the more compute resources or the more memory you can throw at it, the better the simulation you can do, more accurate or more detailed. Similarly, if you're doing a lot of data analysis, the faster you can do that analysis or the more data you can analyze can also be very beneficial in research software. So those are some of the motivations for doing scalable parallel computing. I'll mention that I often refer to this as HPC or high performance computing, which is just a branch of scalable parallel computing that runs on supercomputers. All right, so when I think about scalable parallel computing, there are 2 main concerns that I think we need to think about. And these are things that are key concerns in the Chapel programming language. The first one is parallelism, which is when you're writing your code, what computational tasks should run simultaneously. So again, typically when we write code, maybe we're only running serial code or sequential code and only using a single core. But if we find parts of our program that could run in parallel, maybe the iterations of a loop or some distinct tasks, then if we can identify those, then we could potentially, again, use multiple cores and get some parallelism. The second key concern is locality. And this says things about where things should happen. The first one is, where should tasks run? If I identify these 4 tasks, should they all run on a single compute node, as I'm showing here? Or maybe we should run one of them on each compute node. Or maybe I could actually create even more tasks and run on all of the processor cores on all of my compute nodes. Right, so which tasks and where those tasks should run are kind of the first concern of parallelism and locality. And the second aspect of locality is, where should data be allocated? So as an example, if I have a simple 2x2 data structure I want to store, do I want to store that all on compute node 0? Or maybe I want to distribute that so that each of those elements is on a different compute node? Or maybe I want to replicate it so that each compute node stores the entire data set. And again, that's the other aspect of locality, is where should data be allocated on the system? And again, these are 2 key concepts that we focus on in Chapel. Now, over time, parallel computing has become ubiquitous. Back when I was a student, it was a pretty specialized art. You had to have access to a supercomputer, or maybe your department built a commodity cluster out of some Linux boxes and a network. But generally speaking, not a lot of people had access to parallel computing. Today, we're living in a very different time. You basically can't buy a processor that isn't a multi-core processor, which means we all have parallel computing available on our desktops now. In addition, cloud computing vendors have made large distributed systems very easily accessible to people who have the money to buy the cycles or can convince them to donate them to their project. So in a sense, these supercomputers and commodity clusters of the past are still available today in commercial settings. And I should say, they still exist in kind of the traditional supercomputing settings as well. Finally, GPUs have become a big trend in the last 5 to 10 years, where not only do we compute on multi-core processors, but we're also using GPUs as vector processors essentially to get additional parallelism and additional speed. And what you see today is the largest supercomputers and a lot of the cloud computers, and a lot of our desktops as well for that matter, have GPUs in them, and so that's another option for you to target when you're programming them. When we think about GPUs, I should extend my little cartoon here, because now not only do we have traditional CPU processor cores and memory, but we have these additional GPUs that have their own kinds of cores and memory. And so those are additional places for us to run parallelism, to allocate data, and to worry about locality, not just across the compute nodes, but within a compute node. Do we want the CPU resources or the GPU resources, and which ones? Okay. So with that background, let's talk about Chapel. What is Chapel? To begin with, it's what I call a modern parallel programming language. By modern, what I mean is a lot of the HPC community uses C, C++, and Fortran. By modern here, I mean things more like Java, like Python, like Rust, like Go, like Swift. Kind of languages that are sort of post-C++, if you will. Chapel is designed to be portable and scalable. I can do Chapel development and run Chapel programs on my laptop here, making use of the multiple cores that it has. I can recompile that and run it on a supercomputer, scaling up to the largest supercomputers in the world. Chapel is an open source and collaborative project. We do all of our development on GitHub, and we release under the Apache 2.0 license. We benefit a lot from code contributions from the community, as with any good open source project. And as I've already mentioned, we're very much focused on expressing parallelism and locality. At the highest level, you can think of Chapel as having 2 main goals. The first is to support general parallel programming. You can think of this as, if you have some parallel algorithm in mind and some parallel hardware you'd like to run it on, you ought to be able to do that in Chapel, or we're failing at this goal. The second goal is to make parallel programming at scale far more productive than it is today. Now, this notion of productive means different things to different people sometimes. So let me tell you the way I think about productivity when it comes to Chapel. So the idea is, imagine a programming language for parallel computing whose code is as readable and writable as Python's. And I don't mean to hold Python up as a perfect language, but I think it's hard to argue that it's very, very popular, and that a lot of that comes down to how easy the code is to read and to write. But if you're familiar with Python, Python's support for parallelism is not terrific, particularly at large scales. And a lot of times when you have a Python program that performs very well, if you ask, how does it perform so well? It turns out the answer is that the code was written in C or Fortran, and that Python's just calling out to it. Okay, so where Python is sort of easy to read and write, but maybe isn't great for performance and parallelism, in parallel computing, performance and parallelism are key. So what we want to do is have scalar code that's as fast as traditional HPC languages like Fortran, C, or C++. For the code to be as scalable as MPI or SHMEM, which, if you're not familiar with those, are ways that typical people program HPC systems today. At the same time, I mentioned the importance of GPUs. There are a number of different ways of programming GPUs today: CUDA, HIP, OpenMP, Cocos, and so on. We want to be as GPU capable as those are, so that you can program GPUs in the same language that you program your multi-core CPUs and your distributed memory system. We want to be as portable as C, in the sense that there's no question that you can run it anywhere. And the last one here is we want to be as fun as your favorite programming language. And the idea here is, I think a lot of us get into programming because we think it's a very fun activity. HPC programming is thrilling because you're running on these large systems and potentially running really, really fast or really, really large programs. But I would say that most of the conventional ways of programming HPC systems aren't really fun from a software engineering perspective. So we're trying to restore that, make parallel programming fun again. And creating a language that meets these criteria is our motivation for Chapel. And you'll see a bit today about how well or poorly we're doing this. When we talk about Chapel compared to other languages, one of the ways we compare them is using this scatter plot. There's a lot to take in here, but the main thing you need to know is the further we are to the left here, the further a language is to the left here, the more compact its code is. And this is measured on a website called the Computer Language Benchmarks Game, where a bunch of languages write a bunch of versions of a set of about 10 benchmarks, and you can look at those in terms of how compact the code is or how fast it is. So the further to the left a language is, the more compact it is, and the further down it is, the faster it is. And what you can see here is that the very most compact languages are things like Python and Ruby, but that their performance is much poorer than the languages that are further down on the chart. And those languages are kind of squished together, so it's hard to see them all. But you can sort of see that Chapel and Julia are sort of uniquely down to the left, which means the code is not only compact, but fast. And again, this is sort of a big element of productivity for us. If I zoom in on the bottom part of this plot, so this is the same data, just using a different y-axis, you can see these languages start to distinguish themselves. And you can see that things like C and Rust and C++ are the fastest languages, but you can see that Chapel's quite competitive with them, yet with code that is much more compact than them. So again, this is an indicator that maybe Chapel is succeeding at having code that is both compact and fast. Now, compact doesn't always mean readable, but I would say that if you open up our versions of these benchmarks, you would find them quite readable, particularly compared to some of the fast versions in other languages. I'm not going to spend a lot more time on this comparison, but if you're interested in more details about how we generated this plot and what this data represents, there's a link here on the bottom, and these slides should be available through our website or the YouTube video comments. The one other thing I want to note before going on, though, is that this shows that Chapel is fast and compact compared to conventional languages. This computer language benchmarks game is really only focused on kind of desktop computing, so either sequential computing or multi-core computing. But of all these languages, again, Chapel is one of the very few, in fact, I think maybe the only one on this side, that was designed for large-scale parallel computing, other than perhaps Go, depending on how you think about it. So let's move from just this desktop environment to actually a scalable computing environment. And what I'm going to show you is a couple of reasonably simple computations. These are some benchmarks that are often used in the HPC space. The first one's called Stream Triad, and the second is called Random Access, or RA. And the code I'm showing you here, which you can barely see, is how these kernels would be written using C and MPI and OpenMP, which again are conventional ways of programming supercomputers or doing parallel programming at scale today. If we rewrite the code in these slides in Chapel, it takes significantly fewer lines. And there are a few reasons for this. The first is that the C is just an older language, and it has a fair amount of, I would say, syntactic overhead and sort of low-level concepts associated with it, whereas Chapel, as a more modern language, has learned from a lot of other languages and been able to raise the level of abstraction up to a much higher level. The second part of it is that as a language that was developed with parallelism and scalability in mind, Chapel has abstractions built into it that support things like parallel computing and distributed computing using higher level abstractions than you would get in C by mixing in MPI and OpenMP. I'm not going to walk you through this code in detail, but hopefully when you look at it, you can see that it's fairly straightforward, and if you knew these computations, a fairly direct representation of what the computations are trying to do. So this shows the code is compact and clean, and next we'll look at how the performance compares. Now these are speed-up graphs, or performance graphs. Performance graphs. The x-axis represents the number of locales or compute nodes. In this case, we're going up to 256 compute nodes, and each of those has 36 processor cores. So this is about 9,000 processors we're running on. And again, these are performance graphs, so higher is better. In the first graph, I'm plotting a couple of Chapel versions and the reference version. As you can see, all the lines are more or less on top of each other. This is basically a memory bandwidth benchmark, and happily we're all performing equivalently. So you can see that not only is the Chapel much more compact, but giving you the same performance. In the second case, the Chapel line in blue is getting much better performance than the MPI line in green. And there are a couple of reasons for this. One of them is by writing the computation at a higher level, we actually expose opportunities for the compiler to do optimizations and system-specific optimizations that aren't necessarily available in MPI. Or if you were to do them, you'd have to do much more manually and in a non-portable way, potentially. So this is an example where Chapel is not only more compact, but actually outperforming conventional ways of doing this computation. Now, everything I've shown you so far is benchmarks, both the computer language benchmarks game and this slide. And benchmarks are all well and good, but more importantly than that is that a lot of scientists are writing real applications in Chapel. So this is a slide that contains some of our favorite applications that have been written in Chapel. I mentioned earlier that Chapel is designed to be general purpose, and one of the things I really like about this slide is the mix of different kinds of computations here. We have cases where we're simulating the physical universe, whether that's doing airplane design in the upper left or simulating the formation of dark matter in the upper right. There are some computer sciencey types of computations like branch and bound optimizations, AI, data analysis, graph analytics. And then there's some data analysis computations like this Arcuda one in the upper left. I'm going to take you through some of these in a bit more detail in a bit. But at this point, mostly what I wanted to do is just call out the diversity of different kinds of applications being written in Chapel. So at this point, I want to pause and say, come back to the question, why would someone use Chapel? What would make you think, yeah, I think I should use Chapel? And so some reasons you might do that. First of all, you might want to do parallel and distributed programming, and you might be interested in doing that in a language that was designed for it. I think if you're learning parallel computing for the first time, in many respects, it's easier to learn that in Chapel than it is in some of these conventional techniques used in HPC. The second one is maybe you're a Python or R or MATLAB programmer, but you're running into the performance issues that some of these interpreted high-level languages have. So you need more performance or more scalability. That would be another reason to think about Chapel. The other possibility is that you're already doing parallel computing in a conventional approach, and you'd like a more productive approach or a more integrated alternative. So maybe you're doing multi-core parallelism and you're using OpenMP or pthreads, which are typical ways of doing that. Maybe you're doing GPU programming and you're using one of these technologies I mentioned before, CUDA, HIP, SYCL, Cocos, etc. Maybe you're doing scalable parallel computing and you're using MPI or SHMEM. And if you work in HPC, maybe you're actually using some combination of these things in order to get distributed computing plus multi-core parallelism plus GPU programming. And as you can see, you have to start mixing and matching different programming models together to do that. And in my experience, that can become unwieldy. One of the nice things about Chapel is because it focuses on parallelism and locality, it can handle all these different levels of parallelism in a single language with a single unified set of concepts. And so that can result in cleaner code and easier to understand code and easier to maintain. Now, to give the other side of the equation, I don't want to imply that everything is always perfect with Chapel. So some of the reasons either not to use Chapel or things you should be aware of. So one of them is that Chapel's user community is much smaller than that of Python or C++. We haven't been around as long. We've been working in a more specialized field. And frankly, we haven't really been ready for real user applications until the last 5 or 6 years. That said, the community is growing and the Chapel team is very active and communicative. So despite being a small community, we're a very vibrant community and you will get answers to your questions. Another thing is that the number of libraries in Chapel is much smaller than Python and C++. I think a lot of programmers today have the benefit of being able to pick and choose data structures or algorithms from libraries and sort of glue them together rather than sort of programming everything from scratch. We have a good set of libraries, but nowhere near as large of an ecosystem as Python and C++. That said, one of the ways that users deal with this is we have good support for interoperability that I'll talk about a bit later on. And so calling out to existing libraries is a way of dealing with this issue. You can then contribute those libraries back to Chapel so that other users can benefit from them. Or some users have rewritten standard libraries in Chapel, perhaps getting benefits in doing so from the parallelism and performance. And a third thing is, if you haven't worked in HPC, I would say that HPC software and HPC in general is a bit more rough and tumble than mainstream languages. I sort of think of HPC as kind of NASCAR racing, where the car probably isn't as comfortable and spacious and full of nice features as maybe you're used to with like a Python or something like that. And so it's a little bit more bare bones and kind of, down to the metal. That said, our project's development proceeds at a very fast pace. And if you run into issues or have questions, those typically tend to be resolved very quickly. But again, it's a little bit of a different world if you're used to sort of Python where everything is very mature and it's a massive community, right? All right, so I've just given you some motivation for Chapel. Here's what I'm going to do for the rest of the talk. I'm going to take some of those Chapel applications I showed you and go into a bit more detail with them. Then I'm going to give you some characteristics of Chapel along some of the lines that the organizers asked us to address. I'll give you a quick sample computation in Chapel just to give you a little bit more of a flavor of the language, and then I'll wrap up. So some sample applications. I showed you this slide before, and what I'm going to do is focus in on 3 of these applications, tell you a little bit more about them. And the reason I chose these 3 is I think they're interesting at representing kind of some of the different aspects of the spectrum of applications that people have written in Chapel. So let's focus in on those 3. The first of these 3 is a computational fluid dynamics framework that was developed by researchers at Polytech Montreal. They use it primarily for aircraft simulation, but it can be used for all sorts of things. It's unstructured 3D CFD. And this is the largest Chapel application that we're aware of. It's over 100,000 lines of Chapel. And in practice, they run it on their desktops, which is where they do most of their development. And then when they're ready for a big run, they take it over to an HPC system, recompile it, and run it there. I bring this one up because I think it's an example of sort of classic HPC modeling the physical world. And it's an example of, again, one of the biggest Chapel applications we're aware of. In the middle here is something at the opposite end of the spectrum. This is a case where some researchers wrote about 300 lines of Chapel, used it to do coral reef image analysis, basically to determine the health in terms of biodiversity of a coral reef using satellite images. And this is a case where they're running on desktops, as well as on, again, HPC systems. This group's also used GPUs, and I'll talk about that more in a slide or two. So again, you don't have to write 100,000 lines to get benefit from Chapel. To this group, these 300 lines were kind of revolutionary to the work they were doing. And again, I'll discuss that more in a slide or two. Last case here is interesting. It's code size-wise kind of between the two. It's about 5,000 lines. This is a group that does atmospheric data analysis using the Amazon Tall Tower Observatory. They run primarily on desktops, sometimes with GPUs. So this is a group that, despite Chapel being developed for large-scale parallel computing, has really found great benefit just using it day-to-day on their desktops. For some of them, it's replaced Python and Fortran as their day-to-day languages. And this shows that there's parallelism available everywhere, even just on your desktop. You don't have to have an HPC or a supercomputer to benefit from parallelism and to benefit from Chapel. If you're interested in learning more about these cases, we've been doing a series of blog articles that are interviews with users of Chapel, asking them about what they're doing and how Chapel's helped them and what they would like to see improved. So I've shown some screenshots here of those interviews and pulled out some quotes kind of testifying to the benefits they've gotten from Chapel. I won't read through those, but I encourage you to read through them on your own. And I think this series is a great way to learn more about what people are doing with Chapel. There's a link here at the bottom of the slide. What I'd like to do now, though, is dive into this coral reef image analysis a little bit more. The HiRSE admins said that this seemed like an interesting example they'd like to hear more about. So let's talk about it. As I mentioned, this is an application that measures coral reef biodiversity using high-res satellite image analysis. It's about 230 lines of Chapel code that was written in late 2022. And the initial version of the code was CPU only. The rough concept here is that we're going to take this circular mask that you see in the upper right and scan that across the satellite image to determine sort of how many different kinds of life we think we're detecting within that realm, and use this as an indicator of biodiversity. This was written by Scott Bachman, who at the time worked for NCAR, now works for a startup called Seaworthy. along with colleagues of his at the Coral Reef Alliance. And the reason that they chose Chapel is that they had been using MATLAB and Python. They found it easy to transition from those languages over to Chapel. And in doing so, they got a massive performance improvement. So previously, they had these runs that would take them 10 days to do this analysis. And after writing it in Chapel, they could run it in 2 seconds using 360 cores. The other thing that was cool, rather than, in addition to this massive speed up that it gave them, was that it enabled them to do some unexpected algorithmic improvements. So originally, they had this habitat diversity algorithm that was n by n by p in terms of its computational complexity. And once they got that code running so fast, they realized that they had other algorithms they wanted to try, but they never had any hope of being able to do before that they can now express. So they moved to this more complicated algorithm, spectral diversity, which is order m times n times p cubed. This was a case where the Chapel run was originally estimated to require about 4 weeks on an 8-core desktop, so not a very large system compared to the ones I was talking about in the previous slide. But what they did was they also updated the code to leverage GPUs. This required adding about 90 more lines of Chapel code that took them up to a total of 320 lines. And in this, they were able to run in about 20 minutes on 64 nodes of Frontier, which was using 512 GPUs. So again, I think this is a really compelling example because it shows how groups that had solutions that were working for them but not performing very well were able to write fairly short Chapel codes and get a massive speed up, as well as a great bump in terms of the algorithm that they were able to apply. All right, so that's the end of that. And again, I encourage you to read Scott Bachman's interview with us on the Chapel blog if you're interested in hearing more about this. That link was back a couple slides. Oh, I'm sorry, I forgot there's a graph here. This is a graph showing the speed up as they added nodes. As you can see, the speed up's not linear. We're not getting twice as much performance when we move from 32 nodes to 64 nodes, but it is scalable in the sense that as we're adding resources, we're getting more benefit. We think there's more that could be done to make this code more scalable, but for the purposes of this group, it has been good enough, and so why put in that effort? All right, before moving on, there's one more application I want to talk about, which is Arcuda. This is pretty different than the other applications I've been talking about here, and it may be interesting to people in this community. So what Arcuda is essentially a Python library, and you'll be interacting with this Python library in the normal way. Maybe you're using a Jupyter notebook. And the Python library provides calls that look like familiar NumPy or Pandas calls. But where NumPy and Pandas are typically implemented on the desktop, again, I think using like C or C++, for Arcuda, the calls are actually implemented in Chapel, running out potentially on a supercomputer. And the idea is that every time you type a command, your Arcuda client is going to send that command out to the Arcuda server and run that and then return the result to you. So in practice, this allows you to run, for example, Pandas data frames that are perhaps terabytes in size, much larger than you can ever run on the desktop, and yet in an interactive way and at interactive rates by leveraging parallel computing. So the sort of easy answer to what Arcuda is it's a very scalable version of NumPy and Pandas for data scientists. Now, if you use Pandas, one of the key operations is things like sorting or group by. Sorting is a very expensive parallel computation, and this is a performance graph showing how fast sorting goes in Arcuda. The very top blue line here is showing us running on out to 8,192 compute nodes. This is over 1 million processor cores, and this is sorting 256 terabytes of 8-byte values in about half a minute. This is the fastest sort and the largest sort that I am aware of. If you were a data analyst who has more data than you can fit in your memory and you do a lot of sorting and group bys, I highly encourage you to look at Arcuda as an alternative to other solutions if you want that kind of scalability. The other cool thing about this is that this sort, despite being very performant and very scalable, is implemented using just about 100 lines of Chapel code. So it's also fairly short and sweet. Classically, Arcuda was exactly what I just described to you, NumPy and Pandas that scales. However, the Arcuda framework has been extended so that you can add new operations to it. So if you wanted to do, for example, the satellite image analysis I was just talking about, or FFTs, you could add those operations to the Arcuda server, expose them out to the Arcuda client, and interact with arbitrary computations within this framework. Arcuda is also open source and extensible, so it's something that you could download, contribute to, and branch like any good open source project. And the thing that's really interesting about both these modes of computation is that it's basically a way to drive HPC systems interactively from Python on a laptop, where traditionally HPC systems are interacted with by submitting something to a queue, going, getting lunch, gets through the queue, eventually runs, you check your results, made a mistake, resubmit to the queue, very non-interactive. If you'd like to know more about Okuda, this is a link to its website. You can learn a lot more about it there, including getting over to its GitHub repository. And I mentioned the interview series we've been doing. We've got an interview up there with the co-founding developer of Arcuda, Bill Roos, who talks about how Chapel benefited Arcuda and the benefits that he thinks Chapel brought to the project. All right, that wraps up my discussion of Chapel applications. Hopefully you've found some things here that pique your interest and show you that people have been getting interesting work done with Chapel. Next, I'm going to go through some characteristics of Chapel that we were asked to cover as part of this series. I'm going to break this down initially as 6 key characteristics of Chapel that I often talk about, and then I'll talk about a few more facets that I'm not usually accustomed to talking about. The first one I mentioned already is portable. We've seen this along the way. Chapel runs on laptops, on commodity clusters, on the cloud, and on supercomputers. We can go into this in more detail. The first thing is to know that you don't really have to install Chapel to use it. There are ways that you can use Chapel from within your browser if you just want to try it out before you actually deal with installing it. GitHub Codespaces and Attempt This Online are the 2 ways we have to do that. I mentioned you can run on laptops and desktops. We run on Linux, Mac OS, and Windows if you're willing to use the Windows subsystem for Linux. On HPC systems, we run on commodity clusters, certainly on supercomputers developed by HPE and Cray, our company, and we also run on other vendors' supercomputers. On the cloud, we've run primarily on AWS in practice. In the past, we've run on Microsoft Azure, but it's been a few years since we've done it. I have no reason to believe it doesn't still work, but haven't tried it recently. And Google Cloud, to my knowledge, nobody has ever run on, but again, I don't know of any reason that we wouldn't just run there. Again, just haven't tried it out ourselves. If that's of interest to you, let us know and we can look into it with you. In terms of CPUs, we target Intel, AMD, and several different types of ARM processors. In terms of GPUs, we target NVIDIA and AMD. And we target all of the major networks people use, from high-performance networks like Slingshot down to commodity networks like Ethernet. If you go to the Chapel website, there's a portability page that has all this information and also has this little schematic where you can sort of dial up different aspects of what you're interested in, and this little visualization will show you kind of where to learn about that configuration. If you're interested in getting Chapel, we release it in a number of different formats. You can download the source from GitHub. We also release through SPAC, E4S, Linux packages that you can install with apt and RPM, Homebrew, Docker, modules on HPE Cray systems that you can load, and again, ATO and GitHub Codespaces, which don't require an install at all. The second key characteristic of Chapel I want to talk about is that we're open source. The reason we do this is to reduce barriers to adopting the language and also to leverage community contributions. I've mentioned some of this before, but we are developed at and released through GitHub. We are released and developed under the Apache 2.0 license. Chapel is free to download and use, and the Apache 2.0 license is very permissive. Like any good open source project, we accept open source contributions from the community, and we benefit from those greatly. And I'll mention that we were recently accepted into the Linux Foundation and HPSF, which stands for the High Performance Software Foundation. That's a sub-foundation under the Linux Foundation focused on HPC. The third characteristic of Chapel is that we are a compiled language. So if you're coming from Python, where you're used to dealing with an interpreter and interactivity, Chapel is compiled, and that's to get the best performance possible. That said, as we saw with Arcuda, it's also possible to use Chapel programs in an interactive mode, but the server in the Arcuda case is precompiled. Chapel is statically typed. This means that a given variable x is only going to have a single type for its lifetime, unlike scripting languages where it might be an integer for a while and a string later on. And this is important to avoid simple errors which can occur in dynamically typed languages, and you might only hit those after hours of execution, which isn't usually acceptable in an HPC environment. We're also interoperable primarily with C, C++, Fortran, and Python. I'll talk about this more on this slide. So I think any good modern language is interoperable. No language stands alone anymore. And in practice, as I said, we tend to interoperate most frequently with C, C++, Fortran, and Python. There are two modes in which Chapel can interoperate with other languages. One is a mode in which Chapel owns main, and you can call out to routines in other languages. So for example, if I had a C library that had a routine I didn't want to re-implement in Chapel, I could call out to that and invoke it in C instead. In the second mode, I can build a Chapel library and then invoke it from another language. So if I want to write a parallel kernel in Chapel, I can invoke that from C, for example, and benefit from Chapel's parallelism without having to learn how to do parallel programming in C. If you want to learn more about interoperability, I have a couple of links here. One is to the technical notes about interoperability, part of our project documentation, and the other is for a library that is specific to the case of calling out to Python, which is a use case we've been working on a lot recently. And then popping back here, the very last characteristic on this slide about Chapel I want to cover is that it's a language that was developed from scratch. So where a lot of parallel languages have extended a historically sequential language, Chapel's a language that, again, was designed with parallelism and scalability in mind from the start. That said, if you look at Chapel, you'll see that we've taken inspiration from many other languages, both learning from what they did well and also trying to correct things that we think they did poorly. A couple of other things we were asked to talk about are what kind of tooling is available for Chapel. If you're a VS Code programmer, fortunately, so are a lot of our developers, so the VS Code support is really great, and there's a link here to the plugin you can get to get the VS Code support. For other editors, including VS Code, we have a Chapel language server that gives you a lot of intelligent interaction with your editor about the Chapel code you're writing, making suggestions and pointing out problems and things like that. We have a Chapel linter. We have a program that converts C header files to Chapel extern declarations to help interoperability that I was talking about before. We have Chapel doc that renders documentation for Chapel programs from their comments. We have Python bindings to our Chapel compiler's front end, which can be very useful when you're writing tools that want to analyze Chapel programs. And we have a package manager called Mason. We have other tools as well. These are the ones I think of as the most important and main ones, and you can get more information about these and the others at the link here. We're also asked about testing Chapel code. There are two main ways that people do Chapel testing in practice. The first one is that we have a testing system that is specific to Chapel, and this is what we use to do our nightly regression testing, which involves running hundreds of thousands of tests across many, many platforms. This system supports two modes of testing. There's correctness testing, where we compile and run a program, capture the output of the compiler in the program, and compare that to an expected .good file. If they match, it passes. If they don't, it doesn't. This can also be used in a performance mode where you can track keys like the amount of memory used, the amount of time taken, or the performance, grab the values associated with those keys, and track those over time, either in tabular formats or by plotting them. In this case, I'm showing a benchmark and its performance improving over time. This graph is annotated, so you can see I've sort of popped up here that one of those big upticks in performance was due to this pull request here that changed how large arrays are dynamically allocated. Again, this testing system is fairly specific to Chapel, but it's heavily used by our project, so it's seen a lot of use and has a lot of flexible options. The second option is we do have a unit test package library, which is more like typical unit testing in most languages. If that's what you're looking for, this might be a better option for you. It's sort of more the normal way of doing unit testing, but I would say it's also sort of less full-featured maybe than the Chapel testing system. Chapel documentation, there's a lot of it. The main link is here at the top. This is sort of how you get to the documentation hierarchy as a whole. Some key elements to know about are there's a page called Getting Started with Chapel that has a lot of information about building and configuring your Chapel installation. There's also platform-specific notes, so if you're working on a Mac or AWS, there are files that are just about that platform and give best practices there. There are a bunch of primers, which are essentially Chapel programs that teach specific features and are then rendered as documentation online. I've got the pointers here to some of the standard library modules. We have both standard modules, which are kind of things that ought to be kind of available in any language, and then package modules, which are sometimes user contributed or sometimes things that just don't feel as core, like perhaps a specific file format or something like that. And of course, there's also the language specification, which is a big document describing the language, but sort of the place to go to get the final word on any feature. All right. At this point, I'm going to switch gears. As a programmer, it makes me really uneasy to hear about a language and never see very much code in it. So I'm going to walk you really quickly through a very simple computation, showing you how we can write a serial computation in Chapel, very easily make that into a multi-core parallel computation, and then how we can make it into a distributed memory computation. And to do this, I'm going to use this computation called Bail Index Gather. It's just a very simple kind of computational pattern, and just a really nice illustration that can be explained and written very simply. So the idea here is that I have a source array. I have also a destination array. It may be a different size, as in this example. I'm going to be copying elements from the source to the destination using this set of indices, which say which source element should I grab for a given destination element. And so if I go through these one by one, for the first element, I'm going to look and see, okay, I need element 3. I'll go and read element 3 out of the source array and store that into the corresponding spot. Next, I'll see index 7. I'll go over and grab element 7, store that. And here I'm showing this sequentially, but of course we're a parallel language, so really what we'd like to do is go and do a bunch of these updates simultaneously. So next I'll show you going and reading elements 2 and 7. We go and grab those and store those. And ideally, again, we're doing all of these updates in parallel. The other thing, of course, is we're a scalable language, so we'd also like to do this in distributed memory. And just for my cartoon here, let's pretend I've divided each of these arrays in half. I'm going to run them on 2 compute nodes, though in practice we might run them on dozens or hundreds or thousands of compute nodes. All right, so let's look at some code. I'm going to start out here with declaring a couple of integer constants, n and m. These are going to determine the sizes of my source and destination and indices arrays, which you can see the declarations of here. Basically, the square brackets say what indices should this array be declared over, and then the int says that each element of the array should be an integer. I'm going to elide the code that initializes the arrays, and just show you, here's how we compile the program. The Chapel program is called CHPL, the Chapel compiler. So here we're invoking the compiler, and then we can run the computation using just the executable name, Bail IG. And as I've written it here, well, I'm not really doing much computation. So far, this is just kind of a single core computation. Nothing really parallel about it yet. Let's actually write the Bail Index Gather computation now. Here what I'm using is what's called a zippered iteration. This is when you iterate over multiple things simultaneously. So here I'm saying iterate over my destination array and my indices array, calling the corresponding elements D and I respectively, and then assign to D element I of the source array. So again, this is a for loop, so this is a sequential loop, and this is only going to use a single core of a single compute node, but it'll march through these elements and do the computation as I requested. Now to make this into a parallel program, all I have to do is change this for keyword into a for all keyword. And then I have a multi-core parallel program, which is going to make use of all of the cores on one of my compute nodes. I haven't done anything to distribute the computation yet, so I'm not using my other compute nodes. But again, if I had a 4-core system, this is likely to make the computation go about 4 times faster. Now to distribute the computation, I only have to make a couple more changes. I'm going to do that in 2 steps. The first step is I'm going to name the index sets of my arrays here. So where before I just used the anonymous ranges 0 to n, 0 to m, here I'm going to name those source indices and destination indices, and then declare my arrays over those named index sets. We call these domains in the language. So this is the exact same computation as before, just using some named variables instead of the anonymous domains that I used before. But now that I've named them, what I can do is I can distribute those index sets, which will cause the arrays themselves to be distributed across my compute nodes, and the parallel loop to also be distributed across my compute nodes. So what I'm going to do is use this block distribution library that we provide, and say, create me a block distributed domain. This will take the index sets of my arrays and, again, distribute them across my compute nodes, and also distribute the loops over those arrays across my compute nodes, such that when I run this saying, let's run it on 4 locales, that's what the NL4 means there on my command line, I will use all of the cores on all my compute nodes, and my arrays will be distributed across all the compute nodes as well. You'll also see here on the command line, I threw --n and --m to override the values built into the program and perhaps run on a much larger problem size, which if you're using multiple compute nodes, problem size of 10 and 4 is probably, you probably don't need 4 compute nodes for that. So probably we're running a larger problem size when we're actually running distributed. And I'm going to show you some performance results here running on 4,096 nodes of a Cray EX. Again, this is over 500,000 processor cores. And I'm going to compile this time with these two flags, dash dash fast and dash dash auto aggregation, which basically are just some ways to turn on some optimizations, which are really useful for this program. And this is the performance graph for that. You can see as we scale up to those 4,096 compute nodes, we get better and better performance. If you're wondering about those green lines there that are below the chapel, those are the same computation written in shmem, which is another way of programming parallel systems. Here I'm showing the shmem code for those two versions. As with the MPI code we saw earlier, you can see it's a lot more detail, a lot more complexity. Basically, the programmer has to do a lot more of the work by hand. And not only that, they're not performing as well, and they're actually not able to scale past 512 compute nodes in this case. All right, so with that little example, hopefully I've given you a bit of a flavor of Chapel and how easy it is to turn a serial code into a parallel code into a distributed memory parallel code just by changing some things about the loop and the declarations. So let me now wrap up. To summarize this talk, I hope I've shown you that Chapel is very unique among programming languages. It is a parallel language where most languages have not been traditionally, and it features first-class concepts for talking about parallelism and locality. It ports and scales from laptops to supercomputers. It supports clean, concise code relative to conventional approaches. And as I've mentioned, but haven't really gone into a lot of detail today, other than maybe with the Coral Reef code a bit, it supports GPUs and it does it in a vendor-neutral manner. And as I've shown you, Chapel is being used for productive parallel computing at all scales. Our users are reaping its benefits in practical cutting-edge applications and applying it to domains that are as diverse as physical simulations and data science. And I again want to call out Arcuda as a notable case due to its interactivity, which is unusual in HPC, and the fact that it's extensible, such that if you're a Python programmer or you're supporting a community of Python programmers, it's a way to make your Chapel programs available to them and give them the performance and scalability without leaving the comfort of Python and Jupyter. You're almost certain to have questions that I have not answered in this talk. We're a very interactive community, and so I wanted to tell you about different ways you can interact with us and ask questions. We have a number of live, which in this day and age means virtual community events. We've got a couple of weekly meetings that are public meetings. Our main project meeting is a public meeting. You can join that and hear about how the project is run from week to week, or you can bring up announcements or discussion topics. We also have a weekly slot that's used for a deep dive or demonstration. That's sort of available if we have a topic we want to talk more about, or if you have a big question you want to spend an hour on, or you'd like to review some code with us or do some pair programming. Those are all activities that this slot can be used for. And then on an annual basis, we have a big event called ChapelCon. It was formerly called CHU. That's actually coming in October, and I'll talk about that more in another slide. But we encourage you to attend that. If you just want to keep up with the project, there's some ways that we broadcast information out to the community. We have a blog where we publish articles, typically between 1 and 4 a month. We have a community newsletter we just published yesterday for this quarter. That comes out 4 times a year and just lists kind of big things that have happened and that are coming up in the community. And then for big events like ChapelCon, we have an announcement email list you can join, and that's a good way to keep apprised of, again, big events and have them pushed to your inbox. And then as far as more informal ways to follow us or interact with us, we have social media accounts on most of the major platforms. We have a YouTube channel, and then we have a number of forums that we monitor to interact with users. Discord for kind of chat-based interaction, Discourse for more of a web form or mailing list-based interaction. You can mail us, you can file GitHub issues, you can file Stack Overflow questions that we'll answer. And all of these things are available to you in the footer of the Chapel webpage. So if you want to find your way to any of these, that's the easiest way to get to them. And this is basically just a screenshot of that footer. I mentioned ChapelCon. Again, this is our big annual event. It involves tutorials, office hours, talks from members of the community and from our team. Again, that's coming up in October. This is a free and virtual online event. So if you're interested in attending for an hour or a day or for all 4 days, you're welcome to do that. You can register for ChapelCon today. The details of the schedule are still being worked out. We're currently in the process of reviewing this year's submissions, but we encourage you to join us for that, to learn more about Chapel through the tutorials or the office hours or just by listening to people's talks. And I've mentioned a few times the Chapel website. It lives at chapellang.org. And really everything I've talked about today is available one way or another from the website. So if you only know one URL, this is the one to know. At the end of this talk, if time permits, I will bring up my browser and just kind of introduce you to the website interactively. But I will kind of formally wrap up the talk first. And here I am. So that is my talk about Chapel. Hopefully I've told you a bit about it to let you know what is unique about it, why you might be interested in using it, how you can go about using it. Again, I want to emphasize that we're a very interactive, open community. And if you have questions I haven't answered here, please send them our way. If you'd like to discuss whether or not Chapel would be good for your application or do some pair programming with us, again, those are things we can do on a weekly basis in our deep dive slot or as part of ChapelCon. And we love working with users in that kind of way. So thanks again to the organizer of this series for having us, and thanks for listening. Again, what I'm going to do now is do my best attempt to go over to my web browser and show you a bit about the website, just to help you navigate it. But you can consider that sort of an appendix to the talk. So this is the Chapel website, what you'll find if you land here. At the top, we've got some very simple Chapel applications, or not even applications, Chapel computations to give you a sense of what Chapel looks like. You can select between these here. We've got some key buttons about how you can try Chapel interactively, ways to get it, ways to learn about Chapel. I'll bypass those for now. This is sort of the characteristics of Chapel section. If you click on any of these, it'll tell you more about how we're parallel, why we're scalable, the GPU enabled, things like that. So if you're interested in any of these specific topics, click through to those. We've got some user testimonials. We have some examples of Chapel being used in production, which are some of those applications that I mentioned earlier in my talk. There's links to learn more about each of those. We've got this news section that lists things that have happened recently in the project. I mentioned we just published our latest newsletter yesterday. Here's the registration link for ChapelCon. Here's one of our recent blog articles. Here's another one. Anyway, that's a good way to look for things that are sort of new high-level things. Those are called out on the website. And then down here at the bottom, as I mentioned, are the links to our social media and YouTube channel, to our various discussion and Q&A forums, and different ways you might want to get started with Chapel by downloading it or trying it out. Jumping back up to the top here, installing Chapel or getting Chapel, this download link is your main friend. That's going to take you to this page that lists a bunch of these different download and installation options. If you're already using something like SPAC, Docker, Homebrew, or Linux Package Manager, that's often the easiest way to get started. So for example, on my Mac, I'm a Homebrew user. If I click into this, it tells me that all I have to do is do a brew update and brew install Chapel, and then Chapel will be available to me. Similarly with the other package managers here. If you're using a Linux system, we support Linux packages for a number of different flavors of Linux. And so you can download those. And today we're releasing that as different configurations depending on whether you want a single node or multi-node configuration. I believe in the next release we'll be rolling these all into a single package that you can just download once and then configure which one of those you want. And the complete fallback, the most general way to install Chapel is to download the source code from GitHub, to build it yourself. This is sort of the most general purpose way to install it, I guess I would say. It's also arguably the best way to install it in a way that really customizes itself to your system in terms of what kind of processor and network do you have and things like that. Though the SPAC installation is also sort of a fancy way of doing a source build. So if you're a SPAC user or interested in becoming a SPAC user, this can be sort of a friendlier way of doing the source build where it takes care of a lot of the details for you. So that's a bit about installing Chapel. In terms of documentation, this menu has a bunch of the sort of obvious places to jump into it that I called out on my slides. But if you click here at the top, you'll be taken to the root of the documentation menu. We start with some quick start instructions, which is just kind of like, the fastest way to get started. This using Chapel section is one of the places I link to that just has a bunch of information about prerequisites and how to build it and how to use editors and where to find the man page and things like that. So sort of the basics of getting started with a Chapel installation. Here are the platform-specific notes that I mentioned. There's some technical notes here that can be useful for kind of sometimes esoteric, sometimes core features. Here's a link to the tools that I mentioned. Docs for contributors for people who are developing the compiler and runtime. I won't click into that here. These are the primer examples I mentioned, which go through kind of basics of language or some of the parallel features, locality features, interoperability, and so on. If you have sort of a specific element of the language you want to learn about, this is often, I think, the very best way to learn about those. You could also read the language specification, which is a very big document describing the language in great detail. This is sort of, again, the best place to learn about everything, but it is big and sometimes a bit formal, so the primers can be a friendlier way to learn about things if a primer exists for the specific feature you're looking for. Then we have the documentation for the library modules I mentioned. These are the standard modules. These are the package modules. As you can see, it's a non-trivial number of libraries, but if you compare it to something like what the Python community supports, for example, obviously more modest in size. And there's some important indices here. I guess at the bottom is the documentation index. So this is sort of a good place if you're just trying to find, where would I find documentation on this element? This is the index to the entire documentation hierarchy. Let me go back to the web page and see if there's anything else I wanted to call out there. Except that I disabled my keyboard. Okay. In this resources section, we have things like presentations. This presentation may end up on there. These are separated into featured ones, which we think are particularly good. Featured ones that are focused on applications, short talks, recent presentations, so on and so forth. If you're looking for something specific, like I gave a keynote at HiRSE recently, you can just use your web browser search. It'll search into these and help you find things. If I want to search for all the ones that have videos associated with them, I can do that and sort of pop through and find videos that I might want to watch. So that resources tab is good to know about. The community page has a bunch of the different forums and ways we interact that I talked about in my slides. There's some duplication here with the things in the footer as well. And this is the link to our blog, where you can read all sorts of opinions and experiences and technical things about Chapel. So that's my quick tour of the Chapel website and the resources available to you. Again, if you have any questions I haven't answered here, reach out to us. Happy to answer your questions. Thanks again for watching this video. Thanks again to the organizers of this series for supporting it, and talk to you later on.
Thank you for watching this introduction. Please check out the slides on Zenodo, linked below, and see you next time.